be presenting on a utility scale perspective on reactivity predictions. So I'd like to start by saying that technology is progressing rapidly. The advances in digital tech and scientific innovation, they're converging. So we have innovations happening both from a technology perspective and also from a computational development perspectives. But with this being said, it's actually driving how we understand the nature around us. So traditionally, a few decades ago, the emphasis was quite a bit on trial and error. So it was all like lab-based, observation-driven. We were all gathering data, trying to get insights, coming up with hypotheses on how things work. Slowly with time, as we gathered more and more data, it was all data-driven models. And then we are slowly moving towards knowledge-driven, where we want to move towards first principle modeling, which is where we expect quantum to play a big role. So I don't know if you've heard, quantum seems to be trending these days. But it's actually not a new concept, right? People have been talking about using quantum computers and quantum simulations as a wider story over here. But using quantum computers to do quantum simulations for a long time. Like Feynman suggested this in early 1980s. And this is where we expect like quantum computing to be a game changer as a part of the toolkit for quantum chemistry, which is first principles modeling, where we're able to model nature for what it is without making approximations. Within Capgemini, we'd like to think about how do these solutions come together. So we are working on developing hybrid models, integrating quantum solutions along with classical simulations and machine learning models, getting them all together. And it's not just that. We really do think there is value which only comes from understanding impact end-to-end, thinking about things from atomistic and electronic level all the way to macroscopic level. And this is what brings value. So I won't spend too much time talking about this, but what I would say here is integrating these different models is a really big challenge, irrespective of the field that we're in. So I know we're in the pharmaceutical track, so I'm going to talk about the use case, but I do want to spend a minute emphasizing that we cannot think about these problems or simulations in isolation. We really have to think about where do these problems fit in from an atomistic point and how do they scale across the value chain. So within Capgemini, which is a huge organization, I've been told many actually do not know about Capgemini. So it's a massive organization that employs about 350,000 people. Capgemini's Quantum Lab, we are 40 plus experts who have been working in different aspects of quantum solution development, be it method development for chemistry and materials, be it algorithm development, and how do you actually practically implement solutions, or people working in post-quantum cryptography. But we take over a lot of different projects, including carbon capture, drug discovery, corrosion modeling, battery design, and ester degradation, to name a few. But coming to today's topic, drug discovery. In fact, I think I should request to be speaking after Anders and Matthias every time, because they've done all of this groundwork for me. I don't need to talk about drug development and drug discovery. But I will say that where we expect quantum simulations to actually matter, as Anders, you mentioned this earlier, it's in this very early stage where we expect quantum computers to help with the screening processes. So in the past, as I mentioned this earlier, everything was done either by doing experiments or things were discovered on accident, like penicillin, for example. But can we do this more systematically by using computer simulations? And as we get better with computation simulations, where will quantum computers fit in? I think that's the question that we are trying to answer. So the use case I'm going to be presenting, it's about this targeted covalent inhibitor drugs, or covalent warheads. How many of you here have heard about those systems? 2, 3, 4? So you might not have heard of it, but penicillin, the example that I gave you earlier, it's actually a covalent inhibitor molecule. Same with aspirin, which I had to take this morning because I had a headache. But even though you don't realize it, these class of systems, people interact with them on a fairly regular basis. And this is important for us to have this context in mind. So we do want to ensure that we're able to understand how these drugs operate. And we want to ensure that we're able to create new ones which offer high selectivities, because we want to reduce the total side effects that are present. And we want to ensure that we are able to get the effect that we want just by consuming a smaller dose. But the challenge over here is actually being able to predict the reactivities. So this is overall a summary slide. I'm not going to spend too much time, but we all know that drug discovery is quite challenging. And I do agree that computational aspect of drug discovery, it's a very small portion of it. We're trying to find ways where computers can add value. And one such example is understanding reactivity prediction. So with this in mind, so with GSK, we have been working on this use case for many years. So we have worked on this framework, which we call quantum-centric data-driven R&D framework, where we start with, it's not working even for me, but we start with the system. We think about how do we fragment it, because it's a huge system. We want to break it down. And then we want to select our active spaces. How do we embed our big problem into digestible pieces? And then a key part of our framework is utilizing a quantum fingerprint. This can be different things depending on the use case itself. Come and talk to me at a later stage if you're interested in learning more. But we then feed this understanding into a machine learning model. So it's already a hybrid model that we have developed over the last few years to aid with this prediction. And as you can see, this is a paper from 2023. We have applied this QDDRD approach, where we're able to start with the molecule of interest. We're able to embed it, transform it, generate a fingerprint, run it through a machine learning model for a prediction. But very quickly, we've realized, so this, as I said, like over 2.5 years ago, we've realized that chemistry is complicated. Well, not just 2 years ago. We know that for a while. But for what we wanted to do, the circuits that we want to run, they're quite deep. And that's a massive problem, right? We can't just keep running toy problems, not small molecules. We want to run systems of interest, and we want to get good accuracy. But we've realized that, I don't know if you can see the numbers over here. This is the circuit depth that we had for what some of the systems that GSK was interested in. This is 20,000, 40,000, 60,000, 80,000 circuits. This is for a 16-qubit problem. And that's massive. And we realized that, OK, there's no way we are able to run this. Then what is the approach, right? We had to reevaluate how would we think about reducing the circuit complexities. So I will not have enough time to go over each part of this workflow, but I will break it down into 3 sections over here. So we have a problem of evaluating this real-time evolution, where we start with problem preparation. So this is the basic electronic structure theory problem, which is the foundation of chemistry as we know it. We use some embedding and active space reduction techniques and map our systems. Let me see if it works. Yeah. And then we run a time evolution operation over here over a chosen range. And then we also incorporate reducing the overall Hamiltonian terms. We apply some truncation models. And then we also look at product formula decomposition. So we are thinking about how do we synthesize the circuit right after that. So this is the first stage is preparing the problem in itself. And the details are not important at this stage. I can discuss this at a later time. But we prepare the problem. There are a lot of details from a chemistry perspective that we have to be mindful of. But then once that is done, how do we prepare a circuit that we are able to, that we want to be running, and what are some approximations that we would choose on top of that? And then we want to run this on a real device. So how do we map it onto a device and also run our approximations, which enable us to run this on realistic devices? So I'm happy to report. So these are actually results from January this year. We have been working on getting all of these techniques together, developing the methods behind it. And we have been able to reduce the circuit depth by a significant effect. So this is on an ideal simulation backend, assuming all-to-all connectivity, where without any approximations, you see that the gate circuit depth actually scales quite quickly. It's almost 10 to the 5 over here for the 16-qubit system. But once we apply our techniques that we have been working on, we are able to get almost 29, a factor of 29 decrease in the circuit depth. But this is not just on simulations, right? We also ran this in collaboration with IBM on IBM's Heron architecture. We were able to achieve a 16-fold reduction in the circuit depth and complexities, which we were able to run. But before we actually want to run it, I will point out, so this is exactly the same table as you saw on the previous chart, but I will quickly point out that even though we have reduced the problem size, it's still, in the best of cases, it's still thousands of gates. This is still too big for us to run on today's devices. So we still don't have enough to run these kind of systems. They're not coherent enough to be running these deep circuits. So we started working with Haiku's workflow. So they provide this a range of middleware tools, which is scalable and lightweight. What they're also able to do, which is quite cool, is something called operator backpropagation, where we are able to break down a circuit into chunks that could be executed on device multiple times. So just to give you an example of some numbers, so we ran this without using Haiku's middleware, without using any middleware at all. This is where we were for different problem sizes: 4 qubits, 8 qubits, 12 qubits, and 16 qubits. Everything was all noisy. But once we started incorporating the operator backpropagation and some polytwirling, we see that we could actually get something close to the ideal exact solution over here. So we're actually quite happy with these results. We were able to achieve, I think when we were running this had to be one of the largest ever electronic structure Hamiltonian dynamics calculations performed at that point. So we were able to run this up to 216 2-qubit gates and 371 gates overall in that smaller chunk. But the overall circuit was actually 1,330 gates for this 8-qubit problem. But this is not all. We have been continuing to improve this even further. So we expect to get some results later this year. But what I do want to say over here is it's not about breaking this problem in one small part. This is only a part of a bigger problem. And the question that we're trying to answer is, if you do indeed want to simulate complex chemistry, we have to keep it to mind there are aspects that we need to consider from the electronic structure itself. How do we prepare the problem carefully? And then, once we prepare the problem, how are we transforming it onto a quantum device? And just because we transform it to a quantum device, it still doesn't mean we are able to run it. We still have to consider a lot of different tools. So I guess what I'm trying to say over here is, it's like you want to make guacamole, and you need to pick the perfect avocado, ensure that it's properly ripe, pick all the right vegetables, and ensure that we're ready. But it's not easy. But that's what makes it challenging, and we have to consider all the different aspects surrounding it in order to run anything on a real device today. So I'd like to conclude this work to say that this work, it promises a workflow. So it's not only about this specific system, but it's essentially about the workflow that lets us explore these kind of problems which are relevant to industry. And what we are also planning on doing is, it's not just a circuit reduction technique in itself, but how do we use this that we were able to perform meaningful calculations on today's hardware? And as hardware improves, how does that workflow, how can we enable larger scale calculations in the future, either workflow capable of running that? So this is something that we have been building over the last 2 years, 3 years at this point, working with GSK. And I'd like to end by saying that with a call for action, I think we do need to adopt data-driven R&D. I don't think quantum is going to work just by itself. So the solutions that have to incorporate how would data-driven models work with quantum simulations. Within quantum simulations, where would you use quantum computing and to what extent? And we do need to invest in innovation. We need to allocate resources, whether it's private investments or public funding. I think this is important in order to ensure future breakthroughs. And of course, as like other organizations here, we're also open for collaborations. And we're open to working together on different topics. Come talk to me if you're interested in how can we like take this forward. And finally, yeah, I'll end by saying that we need to like start now. I think quantum chemistry and materials, they really do have an opportunity and potential to transform the world, but we have to understand this impact from end to end. And we have to understand where do benefits actually come from an atomistic scale, and not just say things qualitatively, but how do we quantify it? How do we understand the value? And how are we able to combine different methodologies? And how can we optimize our modeling approach as we have more and more players coming into the game? And overall, how do we integrate atomistic modeling into the entire R&D landscape? And with that, thank you for your attention. And of course, all the work, I'm just a face here. Most of the work here was done by Marek and Vedangi and Vlad. So these are the people who have contributed to this work. With that, I'd like to stop and take any questions.
We have time for a couple of questions. Yes.
Thanks a lot. Just very quick questions. You presented one table which was quite indicative that in your quantum simulations, you, of course, because it's in your simulation of your quantum simulation on a classical computer, so that the ideal case, because it's the ideal case there, it's all-to-all connectivity.
Yeah.
Okay. Now you go on the quantum hardware. Now the question is, why have you selected a quantum hardware which does not have all-to-all connectivity? Because the entire pipeline you've shown, including, let's say, Haiku or other like possible techniques for doing error suppression and error mitigation, like for example, Q control also doing it, could also have done that on an all-to-all connectivity quantum hardware. So I'm just wondering, why have you chosen IBM? Because I believe that you could even have better results with applying your pipeline on another, let's say, device. And not to mention other vendors, but you know what I'm talking about.
Yeah, so I think there are a few layers to your question, and I'll try to address them all. Feel free to re-ask if I missed something. So why IBM? There are like few different reasons. And I do want to like clarify something about, there's a difference between all-to-all connectivity and any-to-any connectivity, which often gets lost in discussions. I think it's important to also consider things like gate speeds and what we are able to run. So this was one of our considerations. And we have been working with IBM as a research partner for a while as well. So there is no like specific reason. And why not run all-to-all? Because it's not easy, and it's also quite expensive to run these calculations. So we rely on partnerships, and with whom we have been working on different projects. And yeah, to run thousands of gates on other platforms without taking any names at this point, it's going to take a lot of time and a lot of money, which we don't have.
Would you be willing to try?
Yeah. I mean, we are, as I said towards the end, we're open for collaborations, and it depends on what we are able to run. And at the end of the day, this is just a workflow that we want to demonstrate. Our goal is like not, at the end of the day, this 8-qubit problem is not going to solve drug discovery, right? What we are interested in doing is developing a workflow that we are able to demonstrate. And we are able to adapt this irrespective of the hardware. We are hardware agnostic in terms of the workflow. So yeah, we're happy to take a look at what the opportunity could be.
Okay.
Yeah. I think there was one more, Stefan?
Run the full circuit versus the reduced circuit? Is it really like transforming only different fluoride-containing mappings, or do you, or anything else, like different border gates, or is it really you cut things out? And then
Can you summarize the question with the microphone? Please?
Yeah.
Thank you.
So just to repeat, was there any trade-offs in the accuracy based on how the circuit reduction actually worked, right? Yeah, I mean the answer is yes. You need to have trade-offs if you want to like reduce the circuits, and this is where we spent a lot of time tinkering with different parts of the workflow. Part of it is thinking about applying things like poly-twirling, and we have the details in the paper. We have the QR code over there for you to like take a look at. But applying techniques and also the Clifford decomposition, where we are able to transform the complex part into like simpler parts and remove the things that are like not needed. And Haiku also has some proprietary parts as part of their optimized execution, where they also remove like parts of the circuit, but it's trading the complexity and accuracy, but enough where we are still able to like, get values that we are able to trust. And that's and we are able to like verify this because this is such a small problem. So we can solve this classically and get a benchmark over there to see, and which is what we've done. And you see that like right here with the approximations, like even operator back propagation, you need to essentially break the circuit into smaller chunks, right? You cut it and you think about how much information loss you have and what are you trading off. And our goal as a part of this entire approach is how do we minimize that loss and maintain the accuracy that we want. So here, as you can see, we ran all of this, the thing in gray. That's done on an ideal simulator, assuming no error, everything was perfect. So with our approximations on a QPU, we were like very, very close over there. So something that we are able to like trust. And yeah, it's still like a work in progress. We are working on further improving it. As I mentioned earlier, these are results from earlier this year. We have been working on improving it even further and improving our overall workflow. So, but I'm happy to chat. As you know, we could have a longer conversation on how do we improve this further.
Okay, let's thank Phalgun again.